Welcome everyone to our Data Science Friday seminar series. I'm delighted to introduce our speaker, Glenn Nofsinger. I'm going to just say a few things about his abstract and his background and then turn it over to him. So his seminar today is entitled Process Query Systems with Applications in Security and Finance. And this is, part of this is about pattern detection problems, which in many ways, the problem is the recognition of high-level behavior in large and noisy data sets. And he'll be talking about Bayesian statistical methods, hidden Markov models, and machine learning techniques as tools for such problems. I'm going to cut this short because someone's cutting a tree in my backyard and it's just so loud. I mean, in my neighbor's yard. Dr. Nofsinger is a data science at Truist Financial Corporation, an American bank holding company headquartered in Charlotte, North Carolina. Previously, he worked as a data scientist at First Hawaiian Bank right here in Honolulu as a member of the Risk Analysis Division. And before entering that position, he spent several years as a principal scientist with BAE Systems in Honolulu, developing image processing, computer vision, and artificial intelligence systems. His work centers on behavior detection using probabilistic methods as opposed to rule-based, and he has designed applications in the disparate fields of sensor networks, social network analysis, image processing, and quantitative finance. He has a bachelor's in science and physics from the College of William and Mary and a PhD in engineering sciences from Dartmouth College. And I was chatting with Dr. Nofsinger with Glenn earlier about his career path. So please feel free to ask questions at the end if you want to discuss, just how did he make his way through into the career that he has now. All right, well, thank you so much for joining us and take it away. Really excited to hear you talk.
Great, well, happy Aloha Friday, everyone. It's Friday night over here in Virginia. We've just gotten through our third ice storm. And I miss Hawaii quite a lot, so this is great to have a virtual visit. I lived in Hawaii for a number of years, and I still consider it my home. So I'm very honored to be here today. And I was going to tell a funny story. So I moved back about a year ago from Hawaii, and I started a new job at a bank here. And my first week of work, was still going through that cultural transition. And I remember talking to one of my coworkers and explaining, it's Friday. So in Hawaii, we take it a little easy. It's a little bit slower. That's called Aloha Friday. And then she looked at me puzzled and she just said, "It's not like that around here." So that was, yeah, that was my, I'm trying to spread as much aloha as I can back here. Okay, so here's what I'm going to talk about today. These are the four topics and sort of four questions that hopefully you will be able to answer by the end of this talk. The first one is, what is a process query system? What is a hidden Markov model? That's a little diagram of a very simple Markov model over on the right. It's a discrete state model. The second question is, how would you use this in a security application? How would you detect normal versus abnormal behavior? And how would you answer a question like, where did this anomaly originate? So part of my PhD work was on chemical plume tracking. If you had a chemical attack in a city, how would you locate where it came from? And then it wasn't just regular smog. Third question, into finance. So say you're working for a hedge fund or someone involved in the financial markets or a government regulator of these markets. How would you detect normal behavior from abnormal behavior, and who did it? And then finally, I'm going to talk a little bit about a current problem I'm working on, which is consumer behavior prediction. So if you're working at a place like a bank, you might be interested in a question like, who will default and when? Or who will buy this product and when? And then I'm going to try to give a little Python demo. There's a star there because of Murphy's Law. Demos just have a high probability of failure. We'll see how it goes. Okay, so what is a process query system? This is a term created by my advisor. His name is George Sabenko. Professor Sabenko at Dartmouth is famous for something called the universal approximation theorem. He's a mathematician from Princeton, and he was able to prove back in the 90s with a fairly famous paper that you can essentially approximate a continuous function with a single layer hidden neural network. And that's kind of a lot of the basis of what we're seeing today with deep learning and those deeper. But George started thinking, what really needs to be done in what are the problem we have today? He was making the analogy of where we stand today with databases is sort of where we were before we had SQL. So he calls this the Aristotelian worldview, is our current approach to data. So we make relationship queries such as and, or, if, then, a member of, not a member of. So similar to Aristotelian logic, where you had a chart of the animal kingdom, phylum, there were strict logical relationships. So if you write a SQL query or a structured data query, these are the same types of queries that you make to your data. Say, show me all packets that were larger than size X that occurred between time A and B, for example. But what he thought was missing was a probabilistic query. So imagine, instead of querying for a rule-based query, like what I just mentioned, imagine a query that said, show me all phone calls I received today that had a probability of being spam greater than 90%. Maybe that's not a good one. Any type of, so after going above the Aristotelian worldview, imagine you have, George called this a Newtonian view. So what did Newton add to the Aristotelian worldview? Added calculus. So going from simple rule-based to the mechanics of calculus, you could then not just make relationships, but you can make statistical arguments and queries. So that's kind of the whole idea of a process query system, is to detect behavior, not using simple rule-based, but rather probabilistic answers can be given back about behavior. And it's based on something called the Hidden Markov Model. So we have here this very poorly drawn diagram by myself that shows a two-state discrete model. And imagine you have state one and state two. So if you hear the term discrete model, it's really just a system where you can express it as a finite number of states. So for example, languages are often modeled with a hidden Markov model. We'll get into the hidden part in just a minute. But a Markov model has a finite number of states, and they produce a sequence. So in this example, we have A, B, B is a set of observations that this discrete model could generate. And this is the way your phone, your Siri or your Alexa, actually takes a sequence of observed syllables. And those syllables are discrete states in a language. And they have certain probabilities of occurring before or after each other, given as probabilities of that language. So for example, English. And that is how voice recognition works. It observes a sequence, it assigns a probability, and then it generates the most likely word that you just said. Okay, so that's at a high level what a process query system is and what a hidden Markov model is. And these are the wider range of applications that this has been used in. So this comes from a paper from IEEE Computer called Process Query Systems. If you're interested, I'm sure you can pull this up from 2007. And Professor Sabenko's students have kind of gone out into the world, some in academia, some in, probably the majority in industry. They work at places like Google. And one of his postdocs, his name is Vincent Burke, took this into computer security. And his company was acquired by Oracle. And they realized the power for looking at computer attacks. So the problem with rule-based computer security is that the number of lines of code in an operating system are growing exponentially. The complexity of the systems we use are growing in complexity faster than we can search them for. So using rule-based, for example, looking for malware and looking for exact signatures in a brute force manner is not scalable. And so you have to find ways to look at not pattern matching, but behavior detection. So in the case of computer networks, what does normal behavior look like? People surfing the web, people checking their email. How does that look different than a worm that is port scanning your network? So that's the application of computer security. Because I was a physics student in a computer engineering department, I got assigned the physics application to this problem. So we had a grant from Department of Homeland Security at the time, and we were concerned about chemical attacks in cities. And so I was given the challenge of, okay, how do you develop a process query system to detect chemical attacks in a city? So we're going to look at that in a couple slides after we go just a little bit of math. So this is a more mathematical version of more concrete of a hidden Markov model. So that the top figure here is a Markov model. So we have our states omega 1, omega 2, omega 3. And those are the transition probabilities. They sum to 1 for a given node. Anyone, this is very popular. If you take a computer science class, you may see a weather example as a classic one. What's the probability of today is rainy, tomorrow is rainy? Of course, if you live in Hawaii, the probability of the weather being good tomorrow is like pretty much 100%. But I always thought the weatherman had an easy job there, except for the years where there were hurricanes or tsunamis. So once we take that basic Markov model at the top, and we go down one, and you'll see the red arrows coming off. So those are called emission probabilities. So that's the hidden aspect. So the idea is that the white circles are your states of your system, but you may not be able to perfectly observe your system. You may, for example, in the case of language, if someone says T, it may actually be a D. So there's a certain probability of observing that sound of it being a T or a D. And once we adapt this into computing and programming, there are 3 fundamental problems that you solve with hidden Markov models. These are the classic 3 problems. The first problem is called the evaluation problem, which is what is the probability that the model produces a sequence of these states? So in that case, you observe a sequence and you say, what's the probability that the model generated the sequence? So you could have a model for the weather in Honolulu. You could have another model for the weather in Washington, D.C., near where I live now. You could give a set of weather and say it was 30 degrees today, and it would say, well, the probability of that coming from Honolulu is practically 0, so it's coming from Washington, D.C. So that would, you could build a weather model for different cities, for example. That's the evaluation problem. The decoding problem is, given a sequence, find the most probable sequence of hidden states. And that's saying you have observed some weather, and you want to know what were the hidden states that produced that weather. Now, this algorithm is very famous. It's called the Viterbi algorithm, is typically used to solve the decoding problem. And Viterbi, the Viterbi School of Engineering is at the University of Southern California. And what Viterbi was famous for, he used this for decoding weak signals. And this was the basis of something called CDMA. So if you have a cell phone produced by Sprint and a couple other companies use that standard, that's what it's doing. So your hidden sequence is a noisy signal. So take your original signal, you add some noise on it. Now your signal is hidden. Can you infer what was the hidden state? The hidden state was what was the original signal that was actually sent. And so that's how the Viterbi algorithm is used to decode noise that gets added into signals. He was very successful with that. And next, and this is the hardest problem, it's called the learning problem. So given a set of observations, how do we learn those probabilities? And like a lot of problems in computer science, this boils down to an optimization problem. So we're trying to determine how do we maximize the probability of this observed sequence given, that's the joint probability, given that we have a set of parameters. So then we're trying to learn those parameters given our set of observations. So this is done with an algorithm called the Baum-Welsh algorithm, also expectation maximization. And that is one of the that's a challenging problem to solve, but fortunately there's some good versions out there. And I'm going to talk about a package you can use in Python that solves this problem. So just to make a little more fun, I came with this example. I apologize for the really poor graphics, but I had to grab some quick free graphics today. So, so I was trying to think of an example for working remotely. Since a lot of us are working remotely these days, you have a colleague, Bob. That's Bob over in the upper right-hand corner, and he lives in some faraway place. And you work with Bob, and you notice he has some mood swings. So some days he's happy, and other days he's kind of grumpy. Well, it turns out Bob is really affected by the weather. You know, he has like a seasonal affective disorder or something. And so you can infer, given your interactions with Bob, that what the weather is, but you can't directly observe the weather because he's remote. He's a remote person, so you don't really know what the weather is where he's working. So to translate those three different problems into this problem, so the decoding problem would be, given a set of moods that you observed this week in Bob, what was the weather in his city this week? So, and then the second problem would be the evaluation problem. So, what's the probability that he's happy all 5 days in a week? And you would build this up over time. You would be able to build a model for that. And then finally, the Baum-Welsh algorithm. How do we build a model to represent Bob? We want to train those parameters so that we can have a model to represent him. And once we build a model for him, we could actually build a model for different people that we work with, and then identify which person it is we're working with. So this next chart just shows what that model would look like. So his moods we can observe. So that's the observed state here. The hidden state is the weather in this case. So what's unique about hidden Markov models compared to other statistical modeling methods is if you look at something like regression or time series analysis that's used in, say, traditional econometrics, we're really just looking at the statistics of the observations. What's fundamentally different about hidden Markov models is we're actually trying to structurally represent the underlying system, and as opposed to just the statistics of the observations. So I think that's kind of neat. So obviously, this is a very simple weather model. You would probably have more than a two-state weather model. But this produces some pretty good results, which I will show into. This is a super simple example, but I just wanted to give something a little fun that would kind of explain those terms a little bit better. Okay, so these are some of the problems that we got assigned in our graduate group to solve using. We built an engine that was solving these hidden Markov models, but we wanted to show that it could be applied to different problems. So the first problem was a physical security camera. So we had a camera, it was an infrared, and we wanted to detect and build models for a normal person walking down the street versus a thief or someone trying to break in a building. And so what we would do is we would have an initial layer doing some image processing where we would detect faces and hands and things like that. And those would become tracks. Those would become observations. And then we ended up building a detector for a normal person versus a thief. So the idea would be that you're detecting that behavior in the video stream. Someone made the point, unfortunately, what we probably ended up building a model for was not a thief, but a graduate student pretending to be a thief was the model we ended up with. But it did work out. The next example was we had some fish in a tank, and we wanted to build behavior models for the different things that fish do. And fish do 3 or 4 different things when they're living in a tank. They eat, they sleep, they fight, and that's pretty much it. So we basically built models for each of those 3 or 4 different activities, and then we would have the camera observing. And this was only 2-dimensional, so it was a little bit crude, but we had a two-dimensional movement model basically. And then at each point in time, those models that had been trained would return a likelihood, saying the likelihood of fighting is 80%, the likelihood of sleeping is 20%. So then we would in real time get a probabilistic number for what are the fish doing right now. Unfortunately, this led to all of the graduate students in the lab having to go through animal training because they considered a webcam on a fish tank as animal experimentation. So that involved a lot of paperwork. I got that job. So we had to certify that we had a guillotine for humane disposal at end of life and stuff like that. Okay, so this is the problem I got assigned, which is the chemical problem, since I was the physics guy, and I wanted to do a little bit of a thought experiment. So imagine you're in a city and you have binary sensors that are in your city, kind of like a smoke alarm. And they're set to go off when they sense some kind of harmful agent. And something gets released. It could either be a fire or it could be an actual attack of some kind. And the sensors start going off spatially in some kind of a pattern. And then you have to answer these questions. Where did it happen? How many sources were there? And are these different observations correlated or are they independent? So this is what it would look like in a really cheesy Matlab simulation. So you start, the blue dots are sensors and they're in an XY space. And then I'm going to step through time. So at time 0, there's no detections. Everything is clear. And then at time 1, oh, we get some there and there. And then at time 2, we get some there. Time 3 there, time 4 there. So then the question is, what happened? Is it coming from one place? Is it coming from two places? So the traditional sort of fluid mechanics, atmospheric science way of solving this would be doing an analytical solution, and this is the diffusion equation in 2 dimensions, which you can solve using differential equations, and you could work it backwards. And this does not really work if you have $5 sensors that are operating thousands of them across the city. So we were looking for a shortcut way to do this without having to solve these really complex sets of differential equations. And so we applied the process query systems. And there's kind of different approaches to how you would solve this. Imagine on one axis you have your complexity of your model, and then on the other axis you have the mobility of your sensors. So some people have proposed to solve this problem with like swarm robots. So these are like little robots that they either swim around the ocean or they drive around the city and they're constantly looking or smelling. And then in the upper right-hand corner, you would have just a few very sophisticated robots. And so the idea is, do you have a lot of really simple things or do you have just a few really complex ones? And then the bottom would be, rather than stationary, you have things that are stationary rather than moving around because they take less energy. So the approach that I took was this approach 3, which is static sensors that are really cheap. It turns out they use a lot less power. So in robotics, 90% of the energy you're going to spend is for motion, moving or flying. And so if you can have something be stationary and sit there, the power consumption can be much, much less. So that's why your smoke alarm on a 9-volt battery can run for like a couple of years. So basically what we did is if we have any Bayesian enthusiasts out there, we applied Bayes' rule, which is a conditional probability. So you're essentially taking that diffusion equation that I showed you before and you're flipping it, you're inverting it. So rather than predicting how particles are going to disperse forward in time, you say, given an observation, what's the likelihood that it came from this area? Sort of like the inverse of, remember when the hurricanes are coming towards Oahu and they're showing forward in time, the area of prediction gets larger and larger. The same thing happens when you look backwards in time. So if you observe something and you look back a short period of time, there's a small area it could have come from. If you go back further in time, it creates a larger cone of uncertainty where it could have originated. So we take these likelihood functions that go backwards in time, and we overlay them. So we take our observations, like at the top, we overlay them, they create a likelihood of where the stuff could have come from. And then we can create queries to estimate where things came from. I'm not going to go, I don't have time, unfortunately. This would be like 2 or 3 entire other talks, but I'm just going to mention a really cool concept that you might want to look at that it's based on. It's called multiple hypothesis tracking. And I just think this is a really cool idea. It originated back in the 60s, and it was used for airline or radar tracking. So imagine you have a set of observations and you have to explain what generated them. So using something called Kalman filtering, if we detect, say, a 747, we can make certain inferences about its possible movements. Whereas if it's a hang glider, it's going to have a different set of potential observations between time points. So these A, B, and C possibilities show that given a set of observations, we could explain them 3 different ways. A is that there's 2 airplanes that just traveling in a straight line. Possibility B is that there's 2 airplanes traveling in a straight line, but that third measurement is kind of an error. It's just a little bit of an outlier, but it's still just 2 tracks. And then possibility C is you have 2 airplanes, but they actually swap tracks. And you're now measuring the 2 different airplanes have swap position. So that multiple hypothesis tracking is sort of at the core of what we were just talking about, because you're maintaining, in this case, you have 3 different hypotheses that can explain the same set of observations. As new observations arise, you can now rank them in likelihood. And you also need to do something called pruning, because it's a combinatorial explosion. Over time, you end up with more hypotheses than you can continue to maintain. But this is part of the whole PQS concept. We maintain multiple hypotheses to explain what we've seen, and we update those likelihoods as new information arrives. Okay, and this is just more kind of simulations. I ended up doing my PhD work in computer simulation because there was a lot of paperwork involved with trying to release chemicals with humans and things like that. So I learned to code more. That was the upside. Once again, this shows sensor observations that receive, and then inverting that into a likelihood of what produced these observations. Same problem that we saw with the speech recognition, just applied to a different area. Okay, let's get out of physics and let's get into something else. So I did not plan on working in finance. It just sort of happened. I was working out in Hawaii. I was working for an aerospace company called BAE Systems, and around 2008, we had this thing called the financial crisis, where a lot of companies almost went bankrupt, and a lot of financial systems were teetering on insolvency. And so after the financial crisis, the Federal Reserve and most regulators around the world got really serious really quickly about running simulations under different scenarios to make sure that your institution would survive if there was another crash. This was called stress testing. So it turned out that there was a huge shortage of people who knew the finance and knew the math. So the group that I was at First Hawaiian Bank, we had oceanographers, we had computational biologists, we had mathematicians, we had computer scientists that were hired, and they just taught us the finance part because we knew how to program, we knew math, and it was really fun. It was a very serious problem, and there was a lot of resources applied to it, and so they built up a group very quickly. And the whole stress testing thing was a really big deal for 3 or 4 years, and still is. But that it was a great opportunity. to learn about financial markets and to combine the engineering and the computer science with finance. And so I didn't plan it. It just sort of happened, and it was an opportunity, and I took it. So it was a good entry. But there was another graduate student in my same group that ended up going into finance. His name is Twardowski, and he's currently in California working for a pretty famous fund called Dimensional Fund Advisors. And his PhD thesis was really interesting. So I don't know if any of you are into stock markets or how stock markets work. There's something called a market microstructure. So if you go home and you want to buy some GameStop stock and you put in an order to buy 100 shares of GameStop, what happens is it gets routed to what's called a market maker. So that there's a handful of these firms, and they're the ones that actually place them. This is an actual picture of the New York Stock Exchange here. So it's basically a server room in New Jersey is what it is. And if you have the resources, your market maker will be located very close to this machine, maybe across the street if you're very fortunate, because you are limited by the rules of physics and the speed of light. And you want your orders to be a few nanoseconds faster than your competitor. So what Twardowski was able to show was that he could de-anonymize trades. So he built processes to represent different types of traders. Now it turns out that your trades, if you place a trade for 100 shares of GameStop, your trade is anonymized to everyone except the government regulator. So because he was working with the government regulators, he had access to this information, and he was able to get ground truth. So if you were to simply look at all of these orders that are placed, so these green dots and red dots show orders that are entered and removed. Most orders never actually go through. They're placed and removed, placed and removed, placed and removed. He was able to look at the timing of the orders that were placed. Using that information and the structure contained in that, he could say, oh, that's Goldman Sachs putting in an order for 10,000 shares. I'm totally making that up. That's an arbitrary name. It could be X, I'll say XYZ. Okay. So it's very, this has applications in both finance as well as computer security. So given time, very, very minute time signature information, he was able to de-anonymize cluster behaviors and say that the actions that happen at this point in time are the same actions that happen at this other point in time by the same actor. And so he built these models, and this was the observation sequence. He was able to assign likelihoods to his models based on the set of observations. So it was pretty cool. So one of the problems I ended up working on was something. There's a Professor Kleinberg at Cornell who wrote an algorithm called the burst algorithm. And he was interested in the problem of, he received all these emails during different points of the year. He received letters about letter of intent from students. He received proposal deadlines. He had notification emails. So he was just swamped with emails, and he wanted to try to figure out if he could develop a chronological temporal information that could then be used to classify the type of email it was. So for example, if it comes in at a certain time of year, there are these bursts. Now, the interesting thing about bursts is they occur in email. They also occur in things like in astronomy, like pulsars. They also occur in stock markets. And so if you're interested in his work, it's super interesting. I highly recommend you checking it out. But I don't have time to go into it right now. I'll just mention that his ideas for classifying email, we were able to apply in financial markets. So the idea of temporal burst structure. And this is one problem that I'm going to show as a burst. So in 2012, there was, and I emphasize was because they went bankrupt after this date, there was a company called Knight Capital. Remember a few minutes ago, I mentioned there was about 5 big players? Well, they were one of those. They had some code that accidentally put millions of orders in at the market open on August 1. So you may have, any of you that worked in finance, there's something called a market order, which means I want to buy the stock and I'll pay whatever it takes. I don't care what the price is, just give it to me. And then there's something called a limit order, which is I will sell it, but I will only sell it at this price. So there was an error in their code. It's actually documented. The SEC did an investigation. You can go back and you can read it. It's pretty fascinating about how mistakes in your code can lead. It's like listed in the top 10 massive failures due to computer code. They ended up losing billions of dollars that morning. Sorry, $460 million that morning. The brokers who were using the software received this cryptic message on their screen that said power peg disabled. And they were like, power peg disabled? What does that mean? So it was this obscure message that didn't really explain what was going on. And this event generated, stocks like Coca-Cola were going from $10 to $40 within a few minutes. And those were the stocks that were on their buy list. There was other stocks on their sell list. So there were stocks that were going from, $80 to $5 in the same period of time. And so the SEC came in, a lot of the trades were busted. Most of the individual investors got the trades canceled and got their money back, but the company went bankrupt. But what it generated was a burst. And so it was a great data set to work on. Similar to a pulsar, similar to a kinematic explosion. It was something that nothing's happening and all of a sudden something big happens. And so how do you detect that? How do you differentiate normal behavior from something that you've never seen before that happens? And so this is the type of behavior that you would like to be able to detect and deconstruct and then pinpoint who did what when. Okay, moving along in finance. Another really interesting problem. It's called adverse selection. I love this problem. It was actually resulted in a Nobel Prize in 1970 called the George Akerlof. So he was looking at information asymmetry. So imagine you're in a market where one side has all the information and you don't. So for example, the used car market, the guy selling the car knows all these problems exist, but you don't, and therefore that's asymmetric. And this creates imbalances, and it ends up hurting everyone because no one trusts anyone. And the reason that a bank cares about adverse selection is the following. So it sounds really boring at first. Your job is to price a loan. So people are coming to you and they want to borrow money, but you don't know how much to charge them. So you're like, well, okay, I want to be a nice guy. I want to charge everyone the same. I want to make it equal. So I'm going to charge everyone the same. Sounds great, but here's the problem. If you charge everyone the same, what happens is the really risky people who would have cost more, they're going to flock to you because they're going to say, oh, wow, this is a great deal. And then the people who are really, very responsible and low risk, they're going to be like, this is expensive. It's not worth it to me. I'm out of here. And so you're going to end up with an entire portfolio of really risky people, and you're going to go bankrupt. And so the problem of adverse selection is appropriately pricing risk. And that's essentially what banks do, is they price risk. And so if your competitor is better at pricing risk than you are, then they're going to win, because they're going to give better prices to the lower risk, and they're going to inappropriately charge people that they shouldn't. And so that's the idea, is to appropriately price risk. And so in behavior modeling, that's a big part of what we do, is given behavior, how do we estimate the probability of default given a certain history? Now there's lots of regulations about what information you can and cannot use to make these decisions. But within the parameters of the information you have available, it puts you on the same playing field as your competitors. So if you're able to identify factors that are still within the legal framework of what you are able to use, then it's win-win, because you're giving someone a good deal that deserves it, and you're lowering the risk, and you're lowering the price for them. And so that's and building trust. And so that's part of what we do at a bank is adverse selection and default modeling. And the way this falls into hidden Markov models is following. If you were doing it, and the same thing applies to corporations as would apply to individuals. You want to figure out what companies have a high chance of making it, what companies might not make it if there's a downturn. So the way companies get rated is as following: AAA, AA, and A. It's kind of like your FICO credit score, but it's for companies. It's the same thing. And so by building a Markov model, you can say, okay, given that this company, and then you can get really fancy, you can build something called a conditional Markov model. So given that this person is currently a AAA, and given that unemployment goes to 12%, and given that GDP drops by 10%, what's the probability they're going to go to single A? So you start building up these conditional probabilities and transitioning. This is also used for modeling the probability that someone's going to, one day be a really great customer, and then 1 quarter from now they're gonna max out their credit card and disappear. Okay, so now we get into the customer behavior application and the demo that will hopefully work. So in customer behavior, this applies to, I'm giving you all some really golden nuggets here, because with these tools, you too could build a process query-like system. It's really, and 2 of the 3 parts actually are already available in free open source packages. So the first part of your problem is you want to isolate your processes. So what I mean by that is, remember when we were looking at the fish, and we had fish that were fighting and fish that were sleeping and fish that were eating. That's called manual labeling. So you would actually have to wait until the fish are sleeping, like catch some video of them sleeping, and then go train your model. Okay, so that's manual labeling, and that works in a lot of cases if there aren't too many different processes. But ideally, and I've become more and more convinced of this in my industry work, you really want to go for, I'm a big fan of unsupervised learning if you can pull it off. So as an example, currently I'm working at a bank. We have hundreds of thousands of customers. We want to find the different types of behavior that they exhibit. There's no way that I can go look through 300,000 accounts and try to identify examples of all the types of behavior. I mean, I suppose if I had like 1,000 interns, maybe we could pull it off. But we really want an unsupervised way to do this. And so I've become a huge fan of using unsupervised learning. Those of you in computer science, I'm sure you're familiar with things like k-means. That's the real basic type of unsupervised clustering. And by using an unsupervised algorithm, you can learn the structure of the data. And I'm also a big fan of that because I'm letting the data speak for itself. So rather than me imposing my view on the data and saying, I think there's probably 4 types of customers, and I think they're the following, I'm going to let the data run the unsupervised algorithm, and it's going to tell me how many types of customers there are. And so that's been very powerful. So for time series, there's this really cool package that I'm a big fan of called Stumpy or Stumpy. And it's this researcher, his name is Law, L-A-W. He works at TD Ameritrade, but his implementation of the package is actually based on the research from a professor at UC Riverside by the name of Keogh, K-E-O-G-H. So he published a number of papers, and the Stumpy package. The other cool thing about Stumpy is that it's been optimized to run on GPUs, distributed processors, so you can scale it up. And what Stumpy does, and I'll show you in just a minute, is it takes time series and it finds what are called motifs. So it finds sections within the time series that are like other sections in the time series, and you get a distance metric. So then you can do something called clustering, and you can find similar groups of people or similar types of behavior in the time series. I'll show you a more concrete example in a minute. But basically, the Stumpy package can be used to take a time series and unsupervised find the different types of behavior. Once you've done that, there's another really awesome package called HMM Learn, which is Hidden Markov Model Learn. And built into this package are those 3 different algorithms that I mentioned, the learning problem, the Viterbi algorithm. So you can do all of that using HMM Learn. So once you have your different sections of your data, you can train models for each of those types and then run the detection problem to detect that behavior in your data. Okay, so now we're gonna get real brave and see if I can do a little code here. Okay. So I thought this was a pretty neat data set. This is passenger taxi data with half-hour increments from New York City. And it's for about 2 months of time. So this shows the number of passengers taking a taxi in New York City. So it's a time series. So first we're going to load up pandas, Stumpy, and a couple plotting libraries. And we're going to load the data set. Okay. So now we ran the Stumpy algorithm, and let me explain real quick what it's doing. This matrix profile is for each, so if you take a sliding window and you move it across your original time series, for each window, this metric tells you the distance, and it's called the standardized Euclidean distance, to the most similar other time point. So it's the distance. So what that means, if you have a spike, that means at that point in time, the closest thing to that thing is not very close. So in other words, there's something unique about this point because nothing else is close to it. So it has a high distance metric from any other point. And when we go back and we check the calendar and we label it, well, you know, if you were to just look at this with the unaided eye, it's a little hard. It's a little hard to see. You can sort of see that one spike that happens, but the others not so much. But when we run the anomaly detector on it, it shows, oh, there's 3 anomalies. And what are those anomalies? Oh, it turns out the first anomaly is Columbus Day. And if we go back, Columbus Day is kind of a big deal in New York City, maybe not in some other places. But the traffic was down. It was a holiday, so there were not as many people taking a taxi at their normal time. Daylight savings time, there was a huge spike. I guess people were running late to work. I don't know. Maybe they normally took the cab or they normally took the bus and they're running late, so they had to call a taxi. And then Thanksgiving, same thing. There's a spike in the minimum distance during Thanksgiving time, and you can sort of see it once you go back to the original time series. You can kind of see it, but it would be hard with to me it would be hard to look at the original data and see that. So by looking for local minima and maxima, you can do things like finding motifs, finding outliers in the time series, and then take these time series, feed them into your training, and look for other periods of time that have that same behavior. This is the window size, just to show you that, you know, a lot of these machine learning algorithms are very parameter sensitive. And to me, that's something to look for, that if I don't put in exactly the right parameters, it's still kind of going to work. So we can see here, we're using a range of window sizes, and it still produces the anomaly detection, maybe not quite as sharply, but it still mostly works. So that's something to be aware of, is how sensitive are your algorithms to these parameter inputs. Occasionally there are algorithms that you have to have everything overfit and exactly set, or else it doesn't work at all. So Stumpy is, if you're interested in time series, check it out. Okay. And then I don't have time today to go into HMM Learn, but basically what that will do is once you've identified your different either outliers or periods of interest, you can feed that into your HMM. You can learn those. And then in the future, when you see that again, it will detect them. Okay, we're short on time. So I have one final slide where I had a few career tips. That's what I called it. Okay. There we go. So I ended up in industry. It wasn't exactly planned. These are just a few little ideas I wrote down from the last few years. So the first thing I wanted to mention is it's important to ask yourself, is it computable? So there's a lot of really cool algorithms out there for machine learning and AI that may not be practical. And especially if you're working in finance or other areas, the data sets can get really big or really complex. And you often have to be able to quickly do some order of n type calculations in your head. Can I, for the computer resources I have, and for the algorithm I want to use, can we do it? and you may have to take your approach and dial it back a little bit and simplify it a little bit. So just as an example, I said, your boss may not want to buy you a GPU cluster. If my boss watches this online, I would love a GPU cluster. Or they may not be willing to buy you 1,000 hours on the Amazon cloud. So that's just a problem that I find in our research group. We run into almost a daily basis. Like, we want to solve this problem. We want to use this approach. Can we actually do it? So over time, you're going to develop some more intuition about which approaches are appropriate for which data sets. And that's a really good intuition to have. So if someone comes to you and says, can you solve this problem? And this is the size of the data. And then you say, well, what's the size of the computer? Yes, we can compute something in a few hours, or no, we can't. So that's a good intuition to develop. The other thing I was going to mention is, if you have an ability or an interest in leadership, there's a huge need for people with technical understanding who are also good with people, who are good leaders. There's a huge lack of people, especially the higher up the ladder you go. Part of it's because machine learning and data science is a new field, so they're just not in the senior positions yet. And I think there's a huge need. They often get taken advantage of by consultants because they just don't know. And so I think there's a huge opportunity down the line in the next few years to take technical skills and also combined with leadership and business skills. Huge opportunity. So I was just going to mention, like, if I was looking for a job, what kind of job would I look for? What kind of, to me, the team is very important. So if possible, I know you don't always have tons of choices, but if you do have choices, I think it's very important to look for a collegial team, a team that works together, where people truly are looking out for the best interest of the team. And I can brag on my team at First Hawaiian Bank because that's the way we were. It was such a wonderful place to be because it was not a top-down approach. It was very collegial. We worked together, sort of an academic type approach where we were all colleagues. We came to consensus decisions as a group, which was really great. So that's something to look out for. Beware of being a loner. You can sometimes end up as the only data science person by yourself, and those that are in charge of managing you may not be able to correctly balance expectations. So they may give unreasonable expectations, or they may not understand why is it taking so long, or so it's good to have at least one or two other colleagues to work with, ideally. we discussed this a little bit at the beginning of the call. I was just saying there are these cycles and kind of hype about, there's something in business called the S curve where things come into popularity and then they go out. So, in the 90s, neural networks was going to solve everything, and then it gets overpromised, and then people say, oh, well, everybody knows they don't work. And so I would just encourage you, don't get too caught up on, getting the exact right title on your degree or the exact right certificates. Just kind of focus on the fundamentals, programming, math, computer architecture, networking, and you'll be fine. So I made the analogy. So during the gold rush of California, the famous story was the people who really made all the money were not the people digging the gold. They were the people selling the picks and shovels. So there's a lot of people out there selling picks and shovels to data scientists, different. So just, focus on the fundamentals. I wouldn't worry too much about chasing, the certain titles. Just learn the stuff and you'll be fine. And then finally, this is a little bit of a more fluffy advice, but I have noticed that attitude is very important. And the people I've met that have been very successful, they're very, not just positive, but they consciously choose to focus on the opportunities of a given situation. You're always going to run into people who are going to tell you why this won't work, what's wrong with the world, why this, just try to keep refocusing your energy on the possibilities and what's possible. And you do need to hear those warning voices sometimes, like, hey, what you're doing is illegal, you really shouldn't do that. Okay, I'll listen to that. But just, try to focus on the possibilities. And that is all I have. And I'd be happy to entertain questions.
Oh, great, thank you, Glenn. That was super interesting. I think so. Folks can either put their questions in the chat or just ask your question. I think we have a good group here today. Any questions for our speaker?
So before people start leaving or asking questions, I just wanted to give a shout out to Lizzie Fink, who is one of our former fellows, who actually suggested that that we invite Dr. Nofsinger to come give a talk. So that's how that connection happened. And so thank you, Lizzie.
Absolutely.
Okay, I'm sure we have some questions here. Well, Glenn, actually, I have one. So I was really interested in applying some of it, the first part of your talk where you're using fish tracking methods to track people and others. Do you see, is that kind of well accepted, because you're taking something that's really kind of basic science, taking those ideas and that valuable research, but twisting it a little bit to apply to a different problem? Because sometimes it's like, oh wow, what is fish tracking going to tell us about anything that's going to be really important to finance, to whatever? But the fish trackers, of course, that's their favorite thing in the world to think about. So do you have other examples or comments around that?
Oh, so in other words, examples of how fundamental problems were adapted to applied problems?
Yeah, exactly.
Oh, too numerous to even mention. I mean, I think I mentioned, computer security and virus detection. So the same concept was applied to finding computer worms, and was commercialized into a huge company. Social network. So, for example, another colleague of mine was working on applying this to. I didn't get a chance to talk about the social networks. So one of my friends, actually, he ended up working on the Enron data set. So I know some of you are probably too young to remember there was a company called Enron back in the day who was very bad and went bankrupt. It was on the cover of like Time magazine one year as like best investment ever. And it turned out to be, the whole company was a fraud. and they were doing fraudulent accounting. And once they collapsed and went under, many Americans lost a lot of their money because they had their stock invested in it. And it's the best example as to, if you ever work for a company, you should not put your retirement account in stock with that company. Because if the company goes bankrupt, you not only lose your job, you also lose your retirement. Anyway, that's a different topic. But my friend was, because this company, many of them went to jail and so forth, they created a really interesting data set. So the data set was an email. So my friend ended up working at the FBI. I can't really say his name or anything like that, but he did work on the Enron data set, and using these methods, they were able to take, he was able to show, given an anonymous email stream over time of people sending email to each other, he could de-anonymize which people were ringleaders versus which people were followers versus which people, like what role they played. So that's another kind of behavior detection example of taking email streams and then trying to infer types of behavior.
I still keep hoping that Gmail will come up with a better way to like automatically answer our emails, or at least cluster them. Because that is.
I want to figure out a way to stop getting all of these spam phone calls on my cell phone.
But I think, honestly, one of the things I think everyone will resonate with this. One of the challenging things about email is that there's no order to the messages. It's here's a task, here's a new task, here's someone asking you a question, here's something that you're late on and you got to turn something in really quick. So it's very hard to kind of have anything other than a really disjointed kind of work session when you're kind of going through your email.
Definitely.
That's a problem. Not sure we have a solution to it. Yeah. There, now we can see Lizzie. Lizzie, do you have a question? Maybe?
I'm so sorry, my audio cut out about 5 minutes ago. I do not have a question, but I'm really grateful to Dr. Nofsinger for speaking to us. Really enjoyed it.
Very good. Well, thank you for inviting me. I really enjoyed it. And if you all have any questions or, career advice questions, feel free to email me. I have a website. If you just Google my name, you'll find it, and you can contact me there. And I would be happy to give feedback about, transitioning from academia to industry or data science careers, whatever.
That would be awesome. Laura, maybe that's something fun we could do with the fellows, bring all the fellows back together and kind of, for a little alumni gathering and talk with some folks like Glenn and others about career prospects. I think that might be really fun.
Yeah.
We're now actually in our third cohort of data science fellows. So we've got about, a good group now. And I think the most interesting, well, the data science fellows is really specifically designed to bring together students of very different backgrounds. So astronomers, oceanographers, some computer scientists, and others, as a cohort to kind of share the experience and see what they can learn from each other too. So we also learn a lot from those different perspectives, with kind of data science and analytics being the common theme through all the fellowships. So
I think I mentioned our data science team at First Hawaiian Bank. If you were to pick the single largest background, it was actually oceanographers.
Okay. I just keep hearing things like this. So the other thing we often hear is that there are no unemployed astronomers too. Astronomers, oceanographers, and others. So I could just tell everyone there's life after graduate school. Even if you didn't.
Absolutely.
And honestly, not everybody wants to be a professor.
We're not all smart enough.
That wasn't what I meant. You should have said different career path. Okay, well, go ahead.
It was a little there was a little bit of challenge transitioning from academia, especially my first job. But then you get used to it, and like anything else, there's pros and cons.
Mhm. Yeah, I bet.
But overall, there's tons of opportunities, and now is a very exciting time to be in data science. It changes every month, like it's so fast. So I think it's really exciting to be in this area right now.
Awesome. Well, any other questions for Glenn before we take off for our weekend? Okay. All right. Well, with that, thank you so much. This was really fun. So I'm just seeing all kinds of comments in the chat. People really appreciated your talk. So feel free to join us anytime. If you want to come and listen to any of our seminars, and if we do have meetings with our fellows, we'd love to have you back. Get some.
Thank you so much. I would like to do that. Thank you. Have a great weekend, everyone.
Okay. All right. Well, aloha.